types of aqueous solutions and solubility. In this paragraph, we will discuss ionic compounds in water, the theory, basically what solubility means. We will continue with the solubility table, and then we will discuss conductivity of ionic compounds in solutions. We will make mention about covalent compounds in water as well. We are going to close the paragraph with strong, weak, and non-electrolytes, both the definition as well as examples. Theory, solubility. Consider the two ionic compounds that we have here, sodium chloride and copper 2 oxide. I would like to point out that the charges that we have here is +1, -1, while the charges that we have at the case of the copper 2 oxide are 2 plus and 2 minus. Based on the Coulomb's law, we have that the energy of the ionic bond, or if you want, the energy of the electrostatic interaction, is directly proportional to Q1 and Q2, and that means the charge of the first ion and the charge of the second ion, and inversely proportional to the distance, to the square of the distance. The distance is between the center of the cation and the center of the anion. Now, because this one here, the sodium and the chloride, have +1 and -1, the energy that we have for the bond or the electrostatic interaction is relatively weak. At this case here, because the copper and the oxygen have +2 and -2, +2 and +2, -2, the electrostatic interaction is much stronger. So, weak, or weaker if you want, electrostatic interaction, and strong electrostatic interaction. Let's speak a little about the water. Basically, we are going to take the ionic compounds, one and another one, 2, and we are going to dissolve them in water. Before we do so, let's examine the nature of water. Water is a polar molecule. Basically, the angle between hydrogen, oxygen, hydrogen is roughly 105. In fact, it's 104.5 degrees. The oxygen, I will use a new word for you, is more electronegative than the hydrogens. Don't worry about that, we will discuss electronegativity at a later chapter. However, what I need from you to remember is that the water molecule at the one side has an electron excess, or if you want, a partial negative charge, and at the side where we have the hydrogens, we have a deficiency of electron density, or if you want, a partial positive charge. So, we take the ionic compounds and we put them in water. Let's see what is going to happen. I will focus first at the case of the sodium chloride. Because the sodium is positively charged, the oxygen that has the partial negative charge is going to interact with the positively charged sodium, and the hydrogens will be farther away. At the case of the negatively charged chlorine, the hydrogens are the atoms that they will be interacting with the chloride, and the oxygens will be farther away. We are going to have exactly the same case at the copper 2 oxide. The oxygens will surround the copper, while the hydrogens will surround the oxygen with a negative charge, the oxide. See the forces that we have here. At the case of the sodium chloride, we have the strong sodium chloride electrostatic interaction. We have a weaker electrostatic interaction between the oxygen of the water and the sodium, and the weaker electrostatic interaction between the chloride and the hydrogens. If we go at the other side, we have this electrostatic interaction between the copper and the oxide. We have this electrostatic interaction between the copper 2+ and the oxygen, and then we have these electrostatic interactions here between the hydrogen and the oxide. Now, This is a weaker electrostatic interaction than the interaction that we have here. So, at the case of the weak electrostatic interaction, a weak bond, the water is going to get between those two and is going to separate them, break them apart. At that case, because the bond that we have between the copper 2 and the oxide are strong, the water will not be able to go inside. Here we are. So, in the solution of the sodium chloride, we are going to have sodium cations that they are going to be surrounded by water, and chloride anions that they are going to be again surrounded by water. The water is going to be differently oriented around the sodium and the chloride. At the case of the strong copper 2 oxide, the water is not going to get in the middle, so the crystal is going to stay as it is and is going to go at the bottom of the solution. So these are going to be floating around. This is going to go at the bottom. Here we are going to have the formation of a homogeneous solution like sugar and water, while at this case here we are going to have the formation of heterogeneous solution where the copper oxide will deposit at the bottom of your flask, and at the top and above that we are going to have the water. It's going to be like having sand in water. Let's see the chemical equations that we have here. The sodium chloride, S stands for solid. At the solid state, we put it in water and it's going to give you sodium that is surrounded by water, and that's what the AQ means. It's hydrated, it's solvated, plus hydrated solvated chloride anions. At the case of the copper 2 oxide, it's going to be a solid. We are going to put it in water and it's going to stay a solid at the bottom of your flask, of your container. So we are going to have ionic compounds that they are going to be soluble in water, and that means that the ion and the cation are going to separate in solution, and we are going to have others that they are not going to be soluble, and that means that they are going to stay as it is, as a crystal, and they are going to fall at the bottom of your flask. This is how it gets dissolved. Consider this crystal that we have here. This is a sodium, this is a chloride, this is a sodium, this is a chloride, and etc. And the water is coming and removes the ions, the anions and the cations one by one. So this is the solid, and these are the solvated cation and anion that are floating around. At the case of the copper 2 oxide, it's going to stay like this. The water will not be able to remove neither the cation nor the anion. Solubility rules. Despite the fact that your textbook has a set of rules, I wouldn't like you to memorize any one of those. During an exam, you will be given this solubility table, and the only thing that I will expect from you is to be able to read it. See how it works. In this list here, in the first column, we have compounds that they are soluble in water. And in this list here, we have compounds that they are insoluble in water. Of course, there are exceptions. So these compounds here are not soluble in water, but they are insoluble. And this compound here are not insoluble, they are soluble. We are going to see together a couple of compounds. The other thing that I want to bring to your attention is this table refers only to the solubility of ionic compounds. So if you have a covalent compound, you cannot refer to this table. Let's see this compound first. This is silver bromide. First, you're focusing on the anion. It's a bromide. Let's go here and see bromides. The bromides are here in this box. All the bromides are soluble with the exception of these cations here. And guess what? The silver is an exception. So the silver bromide is not soluble in water, but insoluble. Potassium nitrate. Nitrates, the nitrates are here, there are no exceptions, so all of them are soluble. Barium sulfate, what do you think? It's soluble or insoluble? Well, the sulfates are here, all of them are soluble with a couple of exceptions. The barium is an exception, so the barium sulfate is not going to be soluble, it's going to be insoluble. Next one, silver nitrate. What do you think? The nitrates are here, no exceptions, so this is soluble. Lead 2 sulfate. The sulfates are here. The lead actually it's an exception, so the lead 2 sulfate is not soluble. Is not soluble, it's insoluble. Sodium iodide. The iodide is here. We have a couple of exceptions. The sodium is not here, so this is soluble. Ammonium sulfate. The sulfates are here. Ammonium is not an exception, so it's soluble. Calcium sulfide. The sulfides are here. They are all insoluble. We have a couple of exceptions. The calcium is at the 2A, so the calcium is an exception. So this compound here, it's not insoluble, it is soluble. That's it, at least for the time being. We are going to see more examples in the near future. Conductivity. The next couple of slides are kind of theoretical. They are going to help us to see weak, non, and strong electrolytes. An electrical circuit we have here. We have a bulb that is connected to a battery through a switch. When the switch is open, the bulb doesn't light. When we close the switch, the bulb lights. What's the difference between the two experiments? Well, here we have we are interrupting the circuit by air. The fact that it doesn't light indicates that air is not a conductive material. Here we close the switch because from one side to the other we have wire and a conductive material. The bulb lights. Now, why the metal that we have here, the wire that we have here, it's a good conductor of electricity? Because it provides free electrons, or if you want, it provides charge carriers. So if somehow at this case here, at the case of the air, we had free electrons, we had charge carriers, then air will have been conductive as well, but it's not. Now, let's see a little how this is going to apply into chemistry. 3 different experiments. Remember, before we had the switch, and between the switch we had air, or we had closed the switch. Here I take the 2 wires and I connect them at the one side and at the other side of a solution. Actually, it's a pure substance of water. So here I have a beaker with water, and I put one end of the wire into the water and the other end of the wire into the water. The bulb doesn't light. That means that water, it's like air, does not have charge carriers, or if you want, free electrons. Let's go to the next one. Let's see the second experimental setup that we have here. Remember, in the first experiment we have water in the beaker. Now in this one we have water and copper 2 sulfate. I have checked the copper 2 sulfate in the solubility table that I gave you earlier, and it's water insoluble. What does it mean? As soon as I'm going to put the copper sulfate, it will go and it will deposit at the bottom of the flask. So here we are going to have the copper sulfate, and here we are going to have water. A pure substance here and a pure substance here. That's a heterogeneous mixture. Well, the bulb doesn't light either. Let's see the next experiment. Here, instead of putting copper 2 sulfate, we put sodium chloride. The sodium chloride is water soluble. It's going to make a homogeneous solution that is going to have sodium cations, that they are going to be surrounded with water, and chloride anions, that they are surrounded with water. And that's why actually the bulb lights. Why? Because the solution that we have here is conductive. It conducts electricity, because the solution that we have here, it has charge carriers. Basically, the sodium plus and the chloride minus that we have here assist the electrons to go from one side to the other. What's the take-home message? A solution that has ions is going to be conductive. A solution without ions is not conductive. Here we are. These are the charge carriers that I said earlier. Conductivity of covalent compounds in water. We are going to see two different molecules. One is the chlorine, where we have a common electron pair between the two chlorine atoms, and here we have carbon dioxide. We have one or more. We have a covalent bond between the oxygen and the carbon, and we have a covalent bond between this oxygen and the carbon. Now, take it as it is at this point. The oxygen is more electronegative than the carbon, or if you want, the shared electron pair is not going to be exactly in the middle, but is going to be closer to the oxygen. The same at this side here. So here we have an excess of electron density, and here we have an excess of electron density, and on the carbon we have a deficiency. So carbon dioxide, it's a dipole if you want. If I take chlorine and I dissolve it in water, I'm going to have absolutely no interaction between the water and the chlorine. There is no interaction. This doesn't have a charge, it's non-polar, and the water is polar. So there is no interaction between those two. At the case of the carbon dioxide is a little different. The water, the delta plus, is going to interact with the oxygen, with the delta minus. So the oxygen of the carbon dioxide will be surrounded by the hydrogens of the water, the same at the other side here, while the carbon that it has the delta plus will be surrounded by the oxygens, the delta minus of the water. What kind of interaction do we have here? Because this is a dipole and the water is a dipole, we have a dipole-dipole interaction. It's relatively weak interaction at the case of the sodium with the water, or at the case of the chloride with the water, we had an ion dipole interaction. See something? The chlorine is not going to be soluble in water. Basically, it's going to escape very soon because there is no interaction between the water and the chlorine. There is no reason why the chlorine should stay in solution. At the case of the carbon dioxide, we are going to have some solubility because there is some interaction. However, this interaction is going to be weak because the bond that we have here, the electrostatic interaction, is weak. What I would like to point out, despite the fact that the carbon dioxide is soluble in water, is not going to give ions, it's going to stay as it is. The electrostatic interaction that we have here is not going to compete, is not going to break the covalent bond. So, despite the fact that the carbon dioxide is going to be soluble in water, the solution will not conduct electricity. the solution will not have charge carriers. So, let me summarize what we have said. Ionic compounds may be soluble in water or insoluble. When they are soluble, they provide positively and negatively charged species, so the solution is going to be conductive. When the ionic compound is non-soluble, the ionic complex will not break apart, and the solution will not have positive and negative charges or charge carriers. That solution will not conduct electricity. Let me go to the covalent compounds that we have here. The covalent compound may be soluble in water. The covalent compound may be soluble in water, like the carbon dioxide, or insoluble in water. No matter what, the covalent compound will not break apart, will not ionize, as we say. We are not going to have charge carriers, so the solution is not going to be conductive. Okay, let's summarize. Your solute, it may be ionic or covalent. If it's ionic, two cases. It may be water soluble or water insoluble. If it's water soluble, it's going to conduct electricity because you're going to have a lot of ions. If it's insoluble, it's not going to conduct electricity because you're not going to have any ions. Covalent compounds, at least the one we have seen so far, they may be water soluble or water insoluble. They may go into solution or they may not go into solution. That's irrelevant. They are not going to conduct electricity because they do not provide ions to your solution. We are going to see another one class, and those are going to be the highly polar, the very polar compounds, covalent compounds, and those are going to be a different story. Highly polar covalent compounds, we are going to start with acids. Remember when we were discussing about this compound here, hydrogen iodide, we said that we have a different name when it's by itself and different name when we have it in water, where we call it hydroiodic acid. Why? Because here this one breaks in water, while when it's by itself it exists as a molecular compound. When we have it in water, it behaves like an ionic compound. How? It provides a proton and a iodide. It provides an H plus and an I minus. Let's focus on the type of the covalent bond that we have here. Hydrogen is a non-metal. Iodine is a non-metal. Basically, both of them need one electron in order to have the magic number of electrons, or if you want, stable electron configuration. So they contribute one electron each in order to have a shared electron pair. Now, this is a new concept that I have mentioned before, but I never explained. Electronegativity. Electronegativity is something that we are going to see in chapter 9, and I will try to give you a rough idea here. Iodine is more electronegative than hydrogen. Basically, atoms that are closer to fluorine, with the exception of the noble gases, tend to be more electronegative than those that they are farther away from fluorine. What electronegativity means? When it comes to covalent bonding, the more electronegative atom pulls its electron pair closer to itself. What does it mean? This is the electron pair. Can you see? It's not exactly in the middle. it's closer to the iodine. That means we have some electron transfer, but not full transfer. That creates a partial negative charge on the iodine and a partial positive charge on the hydrogen. Do you remember when we had the ionic bond? At that case, an electron left from the sodium and it went to the chlorine. There we had full electron transfer. Here, the electron, here, these two electrons haven't left completely the hydrogen. They have left the hydrogen partially. They are not 100% on the iodine. They are most of the time of the iodine. What does it mean? Very simplistic, someone may say that this electron pair is 20% around the hydrogen and 80% on the iodine. And that's why here we have partial charges. Basically, this kind of bond it's a covalent bond that has some ionic character. We call it polar covalent bond. Now, when we take this compound, the hydrogen iodide, and we put it in water, because the water is a polar solvent, is a polar compound, it further polarizes this bond here. Basically facilitates the electron pair to go even closer to the iodine. So when we have this compound, the polar compound in water, it behaves like an ionic. And it gives us this. Can you see here? I have a greater delta plus when I put it in water. So this compound here behaves as an ionic. Here it behaves as a covalent compound with some ionic character. Here it's more ionic rather than a covalent compound. And that's why it gives us the H plus and the H minus, because in water it behaves as an ionic compound. Let's see a couple of acids where we have similar cases. Hydrogen chloride, hydrogen bromide, hydrogen iodide. X here is one of the three halogens. Be careful, the fluorine is not included. Nitric acid, sulfuric acid. This is perchloric acid. Don't worry about this one here. We didn't discuss the perchlorate, so we are not going to include the perchloric acid either. What does it mean? These acids are strong acids. When you put them in water, they are going to give you protons and the anion. At the case of the sulfur, the same with the nitric acid. It's going to give you proton and a nitrate. At the case of the sulfuric acid, it's going to give you the sulfate and 2 protons, because we have the 2 here. This is only for your information, it's not going to be included in your exams. This is going to give you the perchlorate. This is Cl04 minus and then H plus. 1 mole is going to give you 1 mole of protons. 2 moles are going to give you 2 moles of protons. And that's why they are called strong acids, because they ionize, they break apart 100%. And then we have these acids that you have to memorize them. This is the acetic acid, this is the phosphoric acid, this is the hydrofluoric acid, where they ionize partially. What does it mean they ionize partially? They give only, if you start with 1 mole of phosphoric acid, you are not going to get 3 moles of protons. At the end, you are going to get some protons, and at the same time, you're going to have phosphoric acid as well. So it ionizes, the phosphoric acids ionize it to 1%, 10%, or 30%, or 60%. We have values for that. We get them from tables, don't worry. What I want you to remember is that these acids here give you some protons, but not really a lot of protons. We call them weak acids. Here. Now, this list here and this list here, with the exception of this acid here, needs to be memorized. So you need to know which are your strong acids and which are your weak acids. As we are going to see later on, because strong acids give you a lot of ions, they give you a very conductive solution. Because the weak acids ionize partially, they give you only a few ions, cations and anions. That's why they conduct electricity to an extent, but not to a great extent. Let's see bases now. Bases, we have two kinds of bases. We have the ionic bases and the covalent bases. Base is any compound that when we dissolve it in water, it contains hydroxide. For example, sodium hydroxide, calcium hydroxide, aluminum hydroxide. All these compounds that I have mentioned already are ionic compounds because it's a metal with a hydroxide, and for their solubility you need to look into the solubility table that we saw earlier. For example, it seems here that the sodium hydroxide is water soluble, so it's going to conduct electricity. Here are all the ionic bases, some examples of the ionic bases that they are water soluble, so they conduct electricity. These are the strong bases. Aluminum hydroxide, see? The hydroxide is not here, is not an exception, so the aluminum hydroxide is going to be water soluble, insoluble, so it doesn't provide any ions to the solution, so it doesn't conduct electricity. The solution of aluminum hydroxide doesn't conduct electricity. Another one, base. This is a covalent base, and it's a base that you need to memorize. This is the ammonia. Can you see all these compounds have already the hydroxide in the structure, so it's easy to memorize, it's easy to recognize it actually, you don't have to memorize it as a base. The ammonia does not have a hydroxide in the structure, however it does provide hydroxide into the solution when we dissolve it in water. How? Why? This is the chemical reaction here that describes the basic character of the ammonia. Basically, the ammonia is reacting with the water in order to give ammonium cation and hydroxide. How is that possible? The ammonia is going to pick up a proton, an H+ from the water, and hydroxide is what's left back. Now, the double arrow that we have here, it means partial ionization. It means that the reaction goes at this direction as well as the opposite direction. So at the end, we are going to have ammonia, we are going to have water, as well as ammonium and hydroxide. So the ammonia is a base and it is a weak base. That's something that you need to memorize as well. When it comes to the ionic bases, look at the ionic solubility table to see whether you are dealing with a strong base or not. If it comes to the ammonia, you need to remember that it's a weak base. Let's try to put together all the information we have discussed so far. We have ionic compounds, we have covalent compounds, and then we separate it out acids and bases. Acids are all covalent compounds, bases may be ionic or covalent. Let's start with the ionic compounds. The ionic compounds may be water soluble or water insoluble, and we know where to look for that in the solubility table, that it applies only to ionic compounds. When they are water soluble, they are going to dissolve completely and they are going to give a lot of ions to water. If they are water insoluble, they are not going to break apart and they are not going to give any ions to the water. Covalent compounds. They may be soluble, they may be insoluble in water, and that's irrelevant. They do not break apart, they do not give ions to water. Oh, I would like to point out here that when it comes to the covalent compounds, we have singled out the acids and the base. We have one base. acids. The acids, they may be strong acids or weak acids. When we have strong acids, they are going to dissociate completely, so they are going to give a lot of ions. When they are weak, they are going to give some ions, since they are going to dissociate only partially. Bases. We have the strong bases and we have the weak bases. The strong bases are going to give a lot of ions. The weak bases, that's only one, the ammonia, it's going to give a lot, only a few. So let's focus on the column that I have here at the right, here. The compounds that they dissociate completely in water, they provide a lot of ions, so they conduct electricity because they provide ions, they provide charge carriers. We call these compounds here, we call these compounds here strong electrolytes. The ones that dissociate partially, they provide a few ions to the water. That means they do conduct electricity, but not to a great extent. We call them weak electrolytes. Let's discuss this compound here. These compounds here, they are ionic compounds that they are water insoluble, and all other covalent compounds that they are not acids, they are not bases. These compounds here, they may dissolve in water. These are not going to dissolve. However, they do not provide any ions, so they do not conduct electricity, and we call them non-electrolytes. Consider the statement. Hydrochloric acid is a strong electrolyte. Once I asked the students why is it so, and the student told me that I went at the solubility table, I look at the chloride, here is the chloride, I look at the exceptions, the hydrogen is not an exception, then I go back at the chloride, oh, so that means HCl is water soluble, so it's a strong electrolyte. Do you agree or disagree with that? Wrong. Do you remember the table that we saw earlier? The table that we saw earlier refers to the solubility of the ionic compounds. The hydrogen chloride is not an ionic compound, so you cannot look there for this compound. Be careful, it can get confusing. This is a covalent compound, and because it's a strong acid, that's why it's a strong electrolyte. You have to memorize the strong acids and the weak acids and bases. This is a summary of what we discussed with the last couple of slides. Next paragraph, metathesis or exchange reactions. In this paragraph we will discuss precipitation reactions, acid-base reactions, gas evolution reactions, and then we will close this paragraph with acid-base titrations. Chemical reactions are divided into metathesis reactions and redox reactions. The metathesis reactions are further divided, classified as precipitation reactions or acid-base reactions. Not much explanation about this. The acid-base reaction is going to form a salt, is going to neutralize the two compounds, and it's going to form a salt and water. Here, precipitation reactions. We call them precipitation reactions because we have the formation of a precipitate of a solid. Let's study the general format of the metathesis reactions, also called 1,4 reactions. For a metathesis reaction, we need two ionic compounds, and the reaction takes place in water. Here I have used the ionic compound AB and the ionic compound C and D. In order to write the products, we take the cation from the first compound and the anion from the second compound, A and D, and we put them together. In order to write the second compound, here it is, we pair the cation from the second compound and the anion from the first compound. Basically what we are doing here is we swap partners, the cation from the anion from the second compound and the other way around. Let's see an example. Here we have potassium iodide and silver nitrate. In order to write the products, I take the potassium from here and the nitrate from here. In order to write the other compound, I take the silver from here and the iodide from here. As far as the AQ, it indicates that they are water soluble. I know that from the solubility table. The same for the product here. The S means that it's insoluble. S stands for solid here. You start with the two ionic compounds and you get two ionic compounds. This is a precipitate. Can you see the S over there? That's the solid. This is a precipitation reaction. Another one reaction. This is an acid-base reaction. I take the positively charged hydrogen free from here and the negatively charged hydroxide from here. Also, in order to write, and I have the water. In order to write the second compound, I take the positively charged sodium and the negatively charged chloride. And I have the sodium chloride. This is a strong acid, AQ. This is a strong base, water soluble, AQ. This is water soluble, that's why I put aqueous. Water is a covalent compound. We put an L here for liquid. An acid-base reaction gives an ionic compound and water. Water is a non-electrolyte as a covalent compound. This is a non-electrolyte and this is a non-electrolyte. These are what we call the driving forces. Basically, they pull ions away from the solution. The formation of this pulls away from the solution the silver plus and the I minus, the iodide, while the formation of the water pulls protons and hydroxide ions from the solution. Let's get practical here. Let's practice on a couple of ionic equations, how we write ionic equation. Consider the compound. This is potassium sulfate and calcium nitrate. We put them in water. We said that in order to put together the first product at least, we will need to put together the first cation and the second anion. So, the first cation here is potassium and the second anion is nitrate. The resulting compound when we put together potassium and nitrate is potassium nitrate. This has +1, this has -1, so we are not going to need subscripts. Notice something, the nitrate here has a 2, a subscript 2 outside. And that has to do with the charge of the calcium, that it's 2+. However, here the potassium has +1, so we are not going to need the parenthesis and the subscript. The other compound, we are going to put together the calcium and the sulfate. The calcium has 2+ charge, the sulfate has 2- charge, so we are not going to need subscripts. Here we go. Now, we will need to balance the reaction. Here we have 2 nitrates, here we have 1 nitrate, here we have 2 potassiums, here we have 1 potassium. So we are going to need the 2 in front of the potassium nitrate. Here it is. The reaction is balanced. Now, we are going to write what is water soluble and what is water insoluble, or if you want, what is a strong electrolyte and what is a non-electrolyte. Let's see them one by one. We had potassium sulfate. The sulfates are here, the potassium is not an exception, so this is going to be water soluble. I'm going to write it with an AQ. Next one. Calcium nitrate. If you look at the table, you're going to see that this is water soluble too. Next one. Potassium nitrate. If you look at the table that we have, the solubility table, you will see that this is water soluble too. Next one. Calcium sulfate. This is water insoluble, so this is a solid, this is a precipitate. We put an S outside. At this point, this is the molecular equation. We have completed the molecular equation. What we had to do to write the products, we have two products, to balance it, and then to write to specify whether they are water soluble or water insoluble, or as we say, to write the state. Next, what we are going to do, we are going to list all the ions that we have. What does it mean? This one here is water soluble, so when we have it in water, it doesn't exist in this format. It exists as potassium and as sulfate. So this one here, if I put it in water, it's going to give me two potassiums that they are going to be surrounded with water and one sulfate. Here it is. The next compound is going to give us one calcium and two nitrates. Be careful, you will have to put the AQs here. It means that you have the anion or the cation and it's surrounded with water. This one here, each unit has one potassium and one nitrate. Here it is. However, we have two units. So in front of here, I'm going to put a 2 here and a 2 here. The subscript refers to the nitrate. The subscript here refers both to the potassium and to the nitrate, The last one. This is water insoluble, so it's going to stay as it is. I am not going to break it into ions. Here it is. This reaction is called the total or the complete ionic equation. Now, we need to eliminate the ions that appear at both sides. This, for example, it's the same as this one here. Be careful with something. If in front of the potassium you have 2, you must have a 2 in front of the potassium in the products as well. If you don't, that means you made a mistake somewhere here when you were balancing the equation. Go back and check your work. If you have 2 and 3, you cannot cancel them. You will cancel 2 from here, 2 from here, and 1 is going to stay. We have 2 potassiums and 2 potassiums, 2 nitrates and no nitrates, they are cancelled. The ions that I deleted here are called spectator ions. What does it mean? The ions that I deleted here do not participate in the reaction, they are sitting in solution and they are watching. I'm going to write the rest. Calcium is coming together with sulfate in order to give the calcium sulfate. This is the net ionic equation. So we have 3 equations. The molecular equation, the total or complete ionic equation, and then the net ionic equation. The net ionic equation shows you only the ions that they participate in order to give the non-electrolyte. Here in the total or complete ionic equation, you have all the ions, including the spectator ions. Which are your spectator ions? Potassium and nitrate, not 2 potassiums and 2 nitrates. You need to be qualitative here, not quantitative. Also, I forgot earlier to tell you that the calcium sulfate is the driving force, is the precipitate. The reaction takes place because you have the formation of the non-electrolyte, because you have the formation of the calcium sulfate. Now, we are going to have actually the chance to further discuss the driving forces. Acid-base reactions. Let's see one. We have the reaction of the sulfuric acid. Here it is with a calcium hydroxide in water. Let's write the product. It's going to be the proton from here and the hydroxide from here is going to give us water, and then the calcium and the sulfate is going to give us calcium sulfate. At the next step, we need to balance our chemical equation. Well, we have one calcium, one sulfate, one sulfate. Here we have two oxygens, so most likely we are going to need a 2 in front of here. And if that's the case, we are going to have 4 protons. And if we have 4 protons, then we have 2 here and 2 here. So we do need a 2 here and nothing else. Okay, I would like to point out here that I balance sulfates and sulfates. The oxygen that I had here, I didn't include it with the oxygens that I have in the hydroxide. So when I counted oxygens that I have in the water, I said I have 1 here and 2 here. These oxygens another one time, they were balanced as sulfates. It's easier to balance it that way. At the next step, we need to put the states. Now, this one here is a strong electrolyte. As a strong acid, we put AQ, an ionic compound. Look at the solubility table. This is water soluble. This one here, an ionic compound, water insoluble. And this one is a covalent compound. When it comes to the water, you're going to put an L, a liquid there. Our molecular equation. At the next step, we are going to write the ions of all the strong electrolytes. This one here doesn't exist as sulfuric acid. It exists as a proton and as a sulfate. We have 2 protons, that's why I put the 2 in front of here. This is water, this is aqueous, hydrated, this is hydrated. This is going to break apart since it's water soluble. So 1 calcium and we have a Q over there, and the 2 is going to give 2 hydroxides and we have an AQ over there too. This one here, it's going to stay as it is water insoluble. This is a covalent compound, it's going to stay as it is. This is our total or complete ionic equation. The next one, we need to cancel the spectator ions. There are no spectator ions. In order to write the net ionic equation, we will need to delete any spectator ions. Here we do not have any spectator ions. As you can notice here in the products, we do not have any ions at all. So the net ionic equation and the total ionic equation is going to be exactly the same since we do not have spectator ions. Do we have a net ionic equation? Definitely we have a net ionic equation. If we have 1 or more driving forces, and we have 2 at this case, then we have a net ionic equation. Which is the driving force or driving forces? We said it earlier. This one here, the non-electrolyte, and this one here, the non-electrolyte, is calcium sulfate and water. Notice here, in front of the water, I don't write the 2. The water is the driving force, not 2 molecules or 2 moles of the water, whatever the 2 means here. Why water is a non-electrolyte? Because it's a covalent compound. All covalent compounds, with the exception of the acids and bases, are non-electrolytes. Water is water soluble, however, it doesn't provide ions. Another one example. Here we have ammonium carbonate and sodium sulfate. In order to write the product, we are going to take the cation from here and the anion from here. So one product is going to be ammonium sulfate. The sulfate has 2 minus charge, the ammonium has 1 plus charge. And that's why we have the 2 here, because the sulfate has a 2 minus charge. And the other one is the sodium from here and the carbonate from here. The carbonate has 2 minus charge, the sodium has plus 1 charge. That's why we have a 2 subscript there. Balance the reaction. The reaction is balanced. We have 2 ammoniums here, 2 ammoniums here. We have 1 carbonate, 1 carbonate, 1 sodium, 1 sodium, 1 sulfate, and 1 sulfate. Specify what's water soluble and what's not water soluble. That's something that we see from the solubility table. This one here is water soluble, water soluble. Always your starting material is going to be water soluble. You're safe to write AQ and AQ for the starting material without to look. You will have to look for the product. This is water soluble and this is water soluble as well. This is the molecular equation. This is a little different than what we saw earlier. See something? This is aqueous and this is aqueous. Let me ask you, do we have a driving force here? The answer is no, because in the products we do not have a non-electrolyte. Do we have a reaction? Do we have a net reaction? The answer is no. We are going to see very soon that everything is going to be a spectator ion, and then the net ionic equation is going to be empty. Let's do it. How can we go from the molecular to the total ionic equation? Well, if we are going to break apart the strong electrolytes. The ammonium carbonate is going to give us 2 ammoniums and 1 carbonate. Make sure that you write the AQs. This one here is going to give us 2 sodiums and 1 sulfate. This one here is a strong electrolyte as well, water soluble, 2 ammoniums and 1 sulfate. And here we have 2 sodiums and 1 carbonate. Do we have spectator ions? Yes. The ammonium is a spectator ion, the sulfates are spectator ions, the sodiums are spectator ions, the carbonates are spectator ions. Everything is cancelled. 2 with 2, sulfate 1, sodium 2, sodium 2, carbonate 1, carbonate 1. So we do not have a net ionic equation since we do not have a driving force. So we do not have reaction. Decomposition of carbonic acid. I had some difficulty to say that because carbonic acid actually does not exist. As soon as the compound is formed, decomposes. Consider the reaction. Hydrochloric acid is reacting with potassium carbonate in order to give carbon dioxide, water, and potassium chloride. A very similar reaction we are going to do in the lab as well. This is a metathesis reaction despite the fact that it doesn't seem to be one. Let's see how we are going to do it. We are going to take the hydrochloric acid. Hydrochloric acid as a strong electrolyte is going to give us a proton and chloride. Again for another one time. Do not forget to write the AQ and the AQ. Potassium carbonate, a strong electrolyte as well. So it's going to give 2 potassiums and 1 carbonate. However, in order to write the product, we need only the potassium. What's the product? From here we are going to have the potassium and the chloride, and here we are going to have the proton and the carbonate. Since the carbonate has 2-, we are going to put a 2 as a subscript for the proton. Here it is. Now, the potassium here has 1+ charge, the chloride has 1- charge, so we do not need any subscripts. We had also to balance the reaction here is balanced. However, that will have been the correct metathesis reaction if the carbonic acid was not unstable. What does it mean? Carbonic acid decomposes to carbon dioxide and water as soon as we make it. Here it is. Carbon dioxide is a gas, that's something that you need to remember, and the water is liquid. Both of them. What about this one here, carbon dioxide? Is it a strong, weak, or non-electrolyte? It's a non-electrolyte because it's a covalent compound, right? The same for the water. So both of them are non-electrolytes. So I substituted the carbonic acid with the carbon dioxide and the water. If I had a different reaction where in front of the carbonic acid I had a 2, then I will have to put a 2 in front of the CO2, the carbon dioxide, and a 2 in front of the water, so my reaction is going to remain balanced. At the case of an exam, if it's a free response question, essay type of question, you will have to write this metathesis reaction, and you will need to put actually the carbonic acid in a parenthesis. It indicates that it's unstable. This is the molecular equation. Do we have driving forces? What do you think? Yes, 1, 2. The ions that we have from here are going to be spectator ions. Do you expect a reaction? Do you expect to have net ionic equation? Yes, of course we will have, because we have non-electrolytes. So let's go from the molecular equation to the total ionic equation. We need to ionize strong electrolytes. We will ionize this, we will ionize this, leave it as it is, ionize this. This one here, it's going to give 2 protons, 2 chlorides. This one here, 2 potassium cations, 1 carbonate. This one here, write it as it is, water, write it as it is, this. 2 potassiums, 2 chlorides. Do not forget to write the aqueous for your ions. Spectator ions, the 2 chlorides and the 2 potassiums. So basically the spectator ions are the chlorides and the potassiums. Just the 2 chlorides and the 2 potassiums will be deleted. That's what I meant. This is the net ionic equation. Make sure that you write here the unstable intermediate. It's not even an intermediate, the carbonic acid. Other gas evolution reactions. All the gases that we are going to see here are the result of unstable acids. The decomposition of the acid is going to furnish the gas. We saw this one earlier, right? The carbonic acid decomposes to give carbon dioxide and water. Carbon dioxide is a gas. Also, the sulfurous acid gives us sulfur dioxide and water. Sulfur dioxide is a gas. Ammonium hydroxide, here it is, decomposes, rearranges to give ammonia and water. As long as you remember the carbon dioxide, the sulfur dioxide and the ammonia, the only thing that you need to do in order to come up with the unstable species it's to add water. Metathesis reactions. Summary. In order to have a metathesis reaction, it's absolutely necessary that you are going to form a non-electrolyte as a product. We have seen three types of non-electrolytes. Let's see them. A. Water-insoluble compounds. These are ionic compounds that are not soluble in water. B. Gases. We saw three of those: carbon dioxide, sulfur dioxide, and ammonia. They're the product of decomposition of carbonic acid, sulfurous acid, and ammonium hydroxide. And the last one is water. The water is the product of an acid-base reaction. Acid-base titration. An acid-base titration is a procedure we are using to determine the concentration either of an acid or a base when the opposite, a base or an acid, are known. In this case here, we will determine the concentration of an acid, knowing the concentration of a base. What we will need. The unknown here is going to be the acid. We will need a base of known concentration and an indicator. An indicator is not anything else other than an organic compound that it has a different color in acidic and in a basic environment. It has a different color when we have excess of protons in our solution or excess of hydroxides. It's the same thing as saying in an acidic or in a basic solution. The indicator plays a significant role in the acid-base titration since it provides a visual aid to know when we are supposed to stop, when the reaction is complete. For this experiment, we are going to use an indicator called phenolphthalein. So, in this beaker here, we put hydrochloric acid and phenolphthalein. The indicator that we have used, as any other indicator, is a covalent compound. So it doesn't actually dissociate, it doesn't provide ions into solution. However, the hydrochloric acid is going to provide protons and chlorides. This is an acidic solution because we have excess of protons, of H+. Consider another one solution where we place in sodium hydroxide and the same indicator. The sodium hydroxide, as an ionic compound, water soluble, will dissociate or ionize to give sodium and hydroxide. This is a basic solution since we have excess of hydroxide. At this case here, the indicator is going to react with the acid, and here the indicator is going to react with the hydroxide, with the base. When the indicator reacts with the acid, the color of the solution, the color of the indicator actually, so the color of the solution is clear, colorless. When the indicator is reacting with the base, then we have a pink color for the solution. So, in acid is clear, in base is pink. It doesn't matter how much base you have. Even if you have a tiny amount of hydroxide, the solution is going to turn pink. If you have a lot of hydroxide, it's going to be deep purple or deep red. The color is going to be more intense. However, the color is going to be there. So, we can go from one solution, from the colorless to the pink, and the other way back, the other way around, just by changing the excess of either hydroxides or protons. How can we do that? If we start with a solution that has HCl, the solution is going to be clear. So I start and I'm adding here sodium hydroxide. The sodium hydroxide would react with the hydrochloric acid, with the HCl, up to the point that I will have zero excess of protons. If I add another one drop of sodium hydroxide, then I'm going to have excess of hydroxide and my solution is going to turn pink or purple, depending on how much excess I'm going to have. Now, if I stop the addition of the sodium hydroxide and I start adding HCl, hydrochloric acid, then I'm going to destroy the excess of the hydroxide and I will have excess of proton and my solution is going to be clear. And I can go back and forth like that. An application, an acid-base titration. Let's see an application. We have hydrochloric acid here of unknown concentration. I'm going to take this solution, from this solution here, a certain amount, let's say 10 milliliters, and I'm going to put it in water. At the same time, I'm going to take a couple of drops of the phenolphthalein, the indicator, and I'm going to put it here. So, what do I know about the unknown solution? The only thing that I know, about the unknown acid, the only thing that I know is that I have hydrochloric acid and I have pipetted out, I have measured 10 milliliters. That's all I know so far. In order to be able to calculate the concentration of the HCl, I will need the number of moles that I have in those 10 milliliters. So, let's go further. We do not know the concentration and we are adding a small amount of the indicator. Now, since the solution, the hydrochloric acid, is a strong acid, so it's going to give us protons and chloride. Since it's a strong acid, 1 mole of HCl is going to give us 1 mole of protons and 1 mole of chlorides, if we use 1 mole. Now, because this is an acidic solution, the color of the solution, the color of the phenolphthalein is going to be clear. So the phenolphthalein doesn't have color in an acidic environment. We are going to use a burette. That's a burette. We have used it during our first lab. In here I'm going to have sodium hydroxide. I know the concentration of the sodium hydroxide and I'm going to start adding it drop by drop, slowly, until my solution turns pink. Let's see what is going to happen. Let's follow the process. The sodium hydroxide is a strong base, so it's going to give me sodium cation and hydroxide. Now, the hydroxide is going to go here and is going to neutralize this proton. I'm adding the first drop. The first drop is going to neutralize this proton here. Let's see what we have. So I still have excess of protons, can you see? So I'm adding more sodium hydroxide. Here it is. The second drop, the second portion that I have is going to neutralize the remaining part of the acid. So this solution here, it's not basic, it's not acidic, neither one. So it's going to have the same color. The color of the phenolphthalein is not going to change until I have a very, very small excess of hydroxide. So, by adding another one drop, the last drop of sodium hydroxide, we are going to have a very small excess of sodium hydroxide, and that's enough to react with the indicator in order to give us a pink, a purple solution. Remember, that one was neutral, and I added a small excess, a small amount of sodium hydroxide in order to get this pink color. Now, we can go from the acid solution into a neutral solution by adding a base, and from the basic solution to the neutral solution by adding an acid. It can be any acid. Here we use HCl. You can use sulfuric acid or phosphoric acid or nitric acid or whatever the story is. The process of going from an acidic solution to neutral or from a basic solution to neutral is called neutralization. So, if you have an acid and the problem says we neutralize it, you need to know that we are adding the opposite, the base. This is the neutralization equation. Basically what's happening, if we have excess of protons, acidic solution, we're adding hydroxides. If we have excess of hydroxides, a basic solution, we are adding protons and acid in order to turn into water. Let's see an example here. We have an acid, hydrochloric acid, and we take 300 milliliters from that acid. We do not know the concentration. We say that we need to standardize it. Since we have an acid, we will need a base with a known concentration in order to determine the concentration of this one here. Here it is. We use sodium hydroxide as our base, and in order the color of the solution to turn, we had to spend 50 milliliters. What does it mean that the color of the solution changed, turned from clear to pink? That I used to have acidic and now I have very small excess of sodium hydroxide. That's why we say that the color just turned when I pass the 50 milliliters line for the sodium hydroxide. When I added 50 milliliters of sodium hydroxide. What does it mean that the color just changed? It means that the color just turned from clear to pink. It means that at that point the concentration of the hydroxides, or the number of moles for the hydroxides, is equal to the concentration or the number of moles of the protons that we had at the beginning. Now, this is the neutralization equation. We have hydrochloric acid plus sodium hydroxide gives water and sodium hydroxide. We are going to follow exactly the same scheme that we have done before. We are going to put the quantities that we know at the top, and at the bottom here we are going to have the moles. Our world, the world of chemistry. Here is what we know and what we need to figure out. We know that we have 300 milliliters of this, we don't know the concentration. We know that the color changed when I added 50 milliliters and the concentration it was half molar. What are we doing? We need to take the information that we have and convert it into moles. So we are going to take this information, convert it into moles. From the moles of this we are going to go to the moles of this, and then having the moles and the volume we will be able to we will be able to calculate the concentration. Let's do it. The concentration here is half molar. That means per liter of solution, we don't have a liter, we didn't use a liter, but per liter of solution we have 0.5 moles of sodium hydroxide. So we are going to start with what we have, with 50 milliliters. Since our conversion factor has moles per liters, I changed this one here, I changed the milliliters into liters. So I have 50 times 10 to the minus 3 liters times the concentration. I did my calculation, it's 25 times 10 to the minus 3 moles of sodium hydroxide. So that many moles of sodium hydroxide I had to add for the color to change. The mole ratio between the HCl and the sodium hydroxide, the hydrochloric acid and the sodium hydroxide, is 1 to 1. If I had to use 25 times 10 to the minus 3 moles of sodium hydroxide, that means that I had in my solution the same amount, the same number of moles of HCl. This is our conversion factor. The moles of sodium hydroxide and the moles of sodium hydroxide will be cancelled. The only unit that is left is the moles of HCl. Now I have the moles, I have the volume, I can calculate my concentration. The volume needs to be converted into liters, and that's what I have done here. So the concentration of the initial solution, it was 0.083 molar. Another example. We have 20 milliliters of sodium hydroxide. Let me point it out here. Here it is. We do not know the concentration of this one here, so we need to do a titration. In order to standardize the sodium hydroxide, I will need an acid. So I use a sulfuric acid. It needs to have a known concentration. It was half molar. Now, in order the color to change, I spent 45.7 milliliters of sulfuric acid. I want you to calculate the concentration of the sodium hydroxide. Please pause the presentation and try to do it by yourself. You may, from your handout, look at the previous example. The first thing that you will need to do, is to write your equation between the chemical equation between sulfuric acid and sodium hydroxide. I will see you soon. Okay, here is the reaction. This is a metathesis reaction. It's going to give sodium sulfate and water, the proton with a hydroxide. Here it is. You will need to balance it. You have a 2 here and a 2 here. Place all the information that you know and the one that you don't know above the equation. We started with 20 milliliters of sodium hydroxide. We didn't know the concentration. That's why I have the question mark to know what I'm looking for. And then in order to neutralize it, in order the indicator to change color, we had to spend 45.7 milliliters of sulfuric acid, and that was the concentration. We are going to do exactly the same thing as before. We are going to take the information that we have and convert it into moles. As soon as we are going to have the moles of this, I can't calculate the moles of this because the ratio is 1 to 2. So I know the moles of this, I know the volume, I can't calculate the concentration. Let's do it. The concentration is half molar, and that's what I'm going to use. That means that I have 0.5 moles of sulfuric acid per liter of solution of sulfuric acid. That's what I have, 45.7 milliliters, so I start with this, and then I'm using my concentration as a conversion factor. Of course, you can use the equation M, molarity, equals moles over liters. You have the molarity, you have the volume, so you can calculate the number of moles. Liters from here and liters from here will be deleted. The only unit that we have is moles of sulfuric acid, so this times this gives 22.85 times 10 to the minus 3 moles of sulfuric acid. Now, from the moles of sulfuric acid, I will need to go to the moles of sodium hydroxide. I will use the stoichiometric equation. Moles of sulfuric acid need to go down, so it will be cancelled with this. Moles of sodium hydroxide up. In front of the sodium hydroxide we have a 2. In front of the sulfuric acid we have 1. The moles and moles will be deleted, so the only unit that we have is sodium hydroxide. Write it here. Do your calculations. Now, we have the concentration, we have the moles of the sodium hydroxide contained in 20 milliliters of water, of solution, and we want to know the concentration. We will divide the moles over the volume. We need to convert it into liters, so it will be 20 times milli is 10 to the minus 3 liters. Here it is. So the concentration of the sodium hydroxide was 2.28. Questions? That's extremely important. Very often students say to me, At high school, I was using C1V1 equals with C2V2. Can I use it here too instead of doing all these complicated calculations? And the answer is no, you cannot use it. Let's see why. When you say C1V1 equals C2V2, basically you want to say the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. The equation C1V1 equals with C2V2, it's the dilution equation and it should be used only for dilution and nothing else. Let's see the problem that we have here. When you take the concentration of the acid and you multiply it by the volume of the acid, you don't really calculate anything else other than the moles of the acid. Concentration equals moles over volume, right? So volume times concentration equals moles. So in this part here you have the moles of the acid, and in this part here you have the moles of the base. What do you say with this equation here? Is that the number of moles of the acid equals the number of moles of the base. Well, back in high school you were dealing with simple cases where that was true. For example, if you have the titration of sodium hydroxide with hydrochloric acid, the mole ratio between sodium hydroxide and HCl is 1:1. So this here, C1V1 equals C2V2, does apply. However, if you are dealing with any other acid and base, for example sulfuric acid and sodium hydroxide, or even worse, phosphoric acid and sodium hydroxide, where the sulfuric acid has 2 protons and the phosphoric acid has 3 protons, this equation here cannot be used. Why? Because the ratio of the acid over the base is not 1:1, but 1:2 or 1:3 or whatever the story is. Okay. I can guarantee you that in your exam, both the term exam as well as your final exam, you're going to have one titration problem. The ratio between the acid and the base will not be 1:1, but it will be different. So this equation here will not be applicable. Do not use it for your homework, so you are not going to have problems later on during your exam. That's it about metathesis reactions, metathesis or exchange reactions. New paragraph, redox reactions. We are going to discuss here definitions, oxidation state, or if you want oxidation number, how to identify oxidizing and reducing agents, and combustion reactions. Redox reactions. We are going to start with ionic compounds. That's something that we have discussed when we were discussing ionic compounds. Do you remember? Back then we were discussing about sodium, a metal that has the tendency to give up 1 electron, and chlorine atom that has the tendency to gain 1 electron. Sodium has 11 electrons. If it loses 1, it's going to have 10, the same as a noble gas, neon. Chlorine has 17. If it gains 1, it's going to have 18, the same as a noble gas, argon. Now, the sodium cation has +1 charge and the chloride has -1 charge, and the oxidation number is +1 for the sodium, -1 for the chloride. So when it comes to ions, the charge and the oxidation number or oxidation state is exactly the same thing. Oxidation number or oxidation state is going to be a little different when it comes to the covalent compounds, because over there we do not have charges. Now, let's go to the reaction that we were discussing earlier. The sodium The sodium is losing 1 electron, the chlorine gains 1 electron. The one that loses 1 electron, we said that gets oxidized. So, if the charge is going up, we say that the element is getting oxidized. At the case of the chlorine, it gains 1 electron and then we say that it gets reduced. If the charge or the oxidation number is going down, we say that the element is getting reduced. Now, the chlorine is getting reduced because the sodium is there. The sodium enables the chlorine to get reduced. So, the sodium is the reducing agent. The sodium is the reducing agent. Let's see the chlorine. The chlorine is the one that enables actually the sodium to get rid of the 1 electron. It enables the sodium to get oxidized. So, the chlorine is the oxidizing agent. The sodium is getting oxidized. The sodium is getting oxidized by the oxidizing agent. So, if something is getting reduced, is an oxidizing agent. And if something is getting oxidized, is the opposite, the reducing agent. Now, a couple of definitions. Upon oxidation, when we have oxidation, the atom loses at least 1 electron, 1 or more electrons. The oxidation number goes up, increases, and then if it's getting oxidized, it's a reducing agent. The other atom will get reduced, so the original is a reducing agent. If we have reduction, then the atom gains 1 or more electrons, the oxidation number decreases, and the molecule is an oxidizing agent. Let me clarify that, despite the fact that your book doesn't. An atom is getting reduced or oxidized, however, it's the host molecule that it's the oxidizing agent or the reducing agent. That's something that we are going to see it later on, and it will become more apparent. Redox numbers when it comes to covalent compounds. Here the background information is a little more complicated. Let me give you an example, and after I will give you the rules. Consider the reaction. Molecular hydrogen is reacting with molecular chlorine in order to give hydrogen chloride. All these three compounds are covalent compounds. See what's happening? Here we have two atoms of hydrogen that they are coming close enough in order to have a shared pair. Each hydrogen is missing 1 electron, so now that they are sharing this pair, they have the right number of electrons, let's say. Two chlorines, each one is missing 1 electron, so if they come close together, each chlorine contributes 1 electron and then they have a shared pair. And let's go at the case of the hydrogen chloride. Each one is missing 1 electron, they have again 1 shared pair. Remember earlier in this chapter we spoke about electronegativity. Electronegativity, it's the tendency of an atom to pull a shared electron pair towards itself. The tendency to pull the electron pair, or if you want electronegativity, it's greater for atoms that are closer to fluorine, where fluorine is the most electronegative atom of the periodic table. Let's go with the first one. No matter what the electronegativity of the two atoms is here, hydrogen and hydrogen is the same. So this pair is going to be exactly at the middle. The same with this one here. No matter what the electronegativity is, it's the same. So the shared pair is going to be exactly in the middle. What does it mean? This one here contributed 1 and it possesses 50% of the pair, because the pair is half of the time around this proton hydrogen and half of the time around this hydrogen here. So it didn't gain or lose anything. The same about these two chlorines. They contributed to one electron, and now each chlorine has 50% of the pair. Let's go here. Chlorine is more electronegative than hydrogen, so the electron pair is closer to the chlorine rather than hydrogen. In order to assign oxidation numbers, we make the assumption that the electron pair is not really shifted, but it's on the chlorine. It belongs to the chlorine. So we make the assumption that we do not have partial electron transfer, but we have full electron transfer. So we consider this compound here to be an ionic rather than a covalent compound in order to make assignment of oxidation numbers. So see what that means. This hydrogen here lost its electron, and this chlorine here gained an electron. So the oxidation number for this one is going to be +1, and the oxidation number for this one is going to be -1, since that this one has lost one electron and this one has gained one electron. This is more or less the idea behind the oxidation number. We are expressing polar covalent bonds. We are expressing covalent bonds as ionic. When we have a shift of electrons, we consider that it's a full shift, full transfer, rather than a partial shift. We are going to see a couple of rules that we have, and then it's going to be easier for you to calculate the oxidation numbers for covalent compounds. Let's see the rules for assigning oxidation numbers. I'm going to make it very simple. You will not really have to memorize them. Let's start. Okay, I'm going to skip this first one. We are going to see it together with the second rule. Let's see what they say. The sum of oxidation number of each atom in a neutral molecule or in a polyatomic ion, it's going to be always equal to the charge. Let me give you an example. Here we have a compound that consists of chlorine and fluorine. So the oxidation number of chlorine plus, no matter what that is, plus the oxidation number of fluorine is going to be equal to the charge. This is a neutral molecule, so the charge is equal to 0. The oxidation number of chlorine plus the oxidation number of fluorine equal the charge. So if you know the oxidation number of fluorine, you can figure out the oxidation number of chlorine and the other way around. Here we have this compound here, nitrate. The oxidation number of nitrogen plus 3 times the oxidation number of oxygen equal -1. Here it is. Oxidation number of nitrogen, 3 times the oxidation number of oxygen, -1. I will skip this one here. When you have a monoatomic ion, then the charge is equal to the oxidation number. What does it mean? When we have sodium plus 1, then the oxidation number is equal to the charge. The charge is +1, the oxidation number is +1. When you have oxygen -2, then the oxidation number is -2, the same as the charge. Fluorine. Fluorine always is going to have -1. See how we are doing it with oxidation numbers. We assign oxidation numbers to the most electronegative atoms, and always we question one and only one element from the compound, and that's going to be the least electronegative atom. Do you remember the rule that we saw here, and I told you that we are going to skip that one? What does it say? Consider the molecular fluorine. At this case, twice the oxidation number of fluorine, X, equals 0. So X, the oxidation number of fluorine, is 0 at this case. And that's what rule 3 says. Any atom in its atomic or molecular form has oxidation number 0. Oxygen. Oxygen, when with it's by itself, like the fluorine here, twice the oxidation number of oxygen equals 0. So the oxidation number of oxygen is 0. If you look at the periodic table, the charge that we have for the oxygen is -2, right? So always the oxygen is going to have -2 oxidation number unless it is with a fluorine. Then the fluorine is going to have -1, and we are solving, we question the oxygen. Halogens, don't worry about that. Most of the time it's going to be -1 unless it's not really unless it's the least electronegative atom in the compound. We are going to see a couple of examples and you will understand. Here, determine the oxidation number for the chromium in the following compounds. Go at the periodic table and see the charge that we have for the oxygen, -2, right? So we are going to set up the equation here, setting the oxidation number of the oxygen -2. So we have chromium is going to be X plus 3 times -2 equal the charge. What is the charge? 0. Here we are. And solve for X. That's the oxidation number of the chromium. Why am I questioning chromium and not oxygen? Why did I say that oxygen has an oxidation number -2 while the chromium has X? It's not because the question says so. Well, look at the periodic table. Which is more electronegative? Let me rephrase my question. Which element is closer to the fluorine, the oxygen or the chromium? The oxygen. So the oxygen is going to get oxidation number the same as the charge that we predict from the periodic table, and we question the least electronegative atom. Another one, this one here. We are going to set the oxygen -2, we will question chromium, so it's going to be twice X plus 7 times -2 equals -2. Solve for X. The oxidation number of chromium here is +6 too. This is a little trickier. Why is it so? Because you cannot make the assumption that sulfur has a -2 oxidation number. See what? This is an ionic compound. It consists of chromium and the sulfate. So can we figure out the charge that we have for the chromium? Well, the sulfate is -2, so the chromium is 3+. The oxidation number and the charge is the same at this case. The oxidation number of the chromium is equal to the charge. Identifying oxidizing and reducing agents. Before you identify the oxidizing and reducing agent, you will need to find the oxidation numbers. Let's start. The oxidation number of the copper is the same as the charge, 0. This is an H+, right? So the oxidation number for the hydrogen here is +1. I will skip nitrogen. The oxidation number of the oxygen is -2. The oxidation number of the copper is the same as the charge, 2+. The oxidation number of the oxygen here is -2. The oxidation number of the oxygen is -2. I will be questioning the nitrogen. The oxidation number of the oxygen is -2. I will be questioning the hydrogen. Let's come back here. Nitrate is NO3 and a negative charge. So the oxidation of the nitrogen plus 3 times -2 equal -1. That means the oxidation number of the nitrogen is +5. Now, Here I have nitrate and here I have nitrate, so this one is going to be plus 5 too. This one here, the oxidation number of the nitrogen, X, plus twice minus 2, that's the oxidation number of the oxygen, equals 0. So the nitrogen here is plus 4. Let's go here. The oxidation number of the hydrogen twice, that means twice X, plus minus 2 equals the charge. So X equals plus 1. Here they are. Now, in order to have a redox reaction, in order to have an oxidizing and reducing agent, you need an atom to change oxidation number as we are going from the reactants to the products. Something must go up, something must go down, something must get oxidized, something must get reduced. So, as we are going from here, nitrogen is going from plus 5 to plus 4. What do you think? Is it getting reduced or oxidized? Is getting reduced because the oxidation number it's going down, it's getting reduced. Let's see for something else now. What? Copper. It was 0 and it goes to plus 2. So the oxidation number is going up. Is it getting oxidized or reduced? It's getting oxidized. Here we are. So this is a redox reaction because something is getting oxidized and something is getting reduced. Redox reactions are coupled reaction. You cannot have two things that they are getting oxidized and nothing reduced. You must have one that is getting oxidized and one that is getting reduced. Now, the one that is getting oxidized is the reducing agent. Now, the nitrogen is getting reduced, so the host molecule is the oxidizing agent. Be careful with that. An atom is getting reduced or oxidized, while the reducing agent or the oxidizing agent is the host molecule. That's something that I mentioned before. Combustion reactions. Combustion reactions is a type of redox reactions. Basically, you take an organic compound and you burn it with oxygen. It's an exothermic, of course, reaction. Here is an example. This is the organic compound, this is the oxygen. As long as you have only carbon and hydrogen, and that's what we are going to have in 101, the product is always carbon dioxide and water. So, when you have a combustion reaction with oxygen of an organic compound that contains only carbon and hydrogen, and that's the only combustion reactions that we will see, the product is carbon dioxide and water. What you will have to do is to balance it after that. Another one. This is the homework for chapter 4. Make sure that you complete the homework before you make a single posting under the discussion board for chapter 4 and you submit the quiz. Have a nice week. I will see you with chapter 5.